I'm your host, Dr. D. Welcome to Math in the House. Today, we're doing Math Analysis, Chapter 8, Section 4, Polar Coordinates, Graphs, and Equations. I'm your host, Dr. D. Okay, in this section, we're going to be talking about polar coordinates. Now, polar is basically the same thing as the trigonometric coordinates, although instead of counting the horizontal as real and the vertical as imaginary, we're still counting the horizontal as x and the vertical as y. And for any point that I can name with an xy coordinate, I can also name it with an r theta, just like before. So let's look at some examples of that before we go on. All right, so if I have a point that's, let's say, 5 away from the center at an angle of 30 degrees, that's where it is. There's my r theta. R theta then would be 5 30 degrees. Now that is a polar coordinate. Now we could change it to rectangular, but we're in polar graph paper right now, so this is your polar coordinate, 5 at 30 degrees. Now, I could also go the other direction. See, this is the 30-degree direction this way. If I go left on this 30-degree number line, then I'm going in the negative direction. So 1, 2, 3, 4, 5, I could call this negative 5 at 30 degrees. Because notice, it's on the 30-degree angle, but it's going left 5. So that's negative 5 at 30 degrees. Now, I could name this a negative also. Because notice, this angle is 30 degrees if I'm going up this way, but it's 210 degrees going that direction. So that means I could name this point negative 5 at 210. Because it's saying go 210 degrees, but then go the opposite direction of the 210 degrees. So that's negative 5 at a 210-degree angle. Now, I could also name this by a negative angle. So I could name it 5 at, how many degrees is it around, all the way from here around to there? Well, notice that's 30 degrees short of 360. So that'd be negative 330. Remember, we count angles positive in the clockwise direction and negative, or positive in the counterclockwise, negative in the clockwise. So I went negative 330 degrees, and I'm at 5. So that's another way of naming that point. Now, I could also, I don't want to do that. Okay. I could also name this 210-degree angle by a negative angle. What's the negative angle to get to there? Well, that's 30 degrees short of 180, so that's going to be negative 150. So negative 150, but notice the point is 5 in the opposite direction from negative 150. That makes it negative 5 at negative 150. So notice what I've done. I've taken a single point right here that's 5 away from the origin at a positive 30 degree angle, and I've said, well, it's also 5 the opposite direction from 210, or it's 5 in the same direction as negative 330, or it's 5 in the opposite direction as negative 150. So I have named one point 4 different ways, and the angles are all between negative 360 and 360. So I've named it with positive positive, negative positive, positive negative, and negative negative. So that's the name of this game. Take any point on the graph and name it 4 different ways with all the combinations of positive and negative between angles negative 360 and positive 360. Okay, so let's do another one. So let's take this angle right here. Yeah, we'll just say the point right there. So what I want you to do is name that all 4 combinations. So go ahead and pause the video, work on it yourself, and then come back and see if you did it right. Okay, welcome back. All right, so, yeah, like I know you paused the video. All right, so we have 4 away from the origin. At what angle? Well, it's 90 straight up plus 30 is 120. So I can name this the 120 degree angle going that way. So that's 4 at 120, positive, positive. Now, let's name it with a negative 4. So I want negative 4 with a positive angle. So what's my positive angle going to be? I'm going to be going down this direction. So what angle is it that's going down that direction? Well, this is 90, 180, 270, plus another 30 is 300. Okay, so that makes this negative 4 at 300 degrees. Because notice, 300 degrees goes down and to the right, but my point is going the opposite direction, so it's negative 4 at 300. All right, now, let's go back to a positive 4 and make a negative angle. So, positive 4, what angle is it that goes around clockwise that far? Well, notice it's 90, 180, and then 60 more is 240. So that's negative 240. So it's a positive 4 at 240. Now, the last thing we want is negative 4 at a negative angle. So basically we need to name the 300 degree angle as a negative. Well, that's just going to go down like this. Well, how far did we have to go? 60 degrees in the negative direction. So there it is. positive, positive, negative, positive, positive, negative, negative, negative. All right, that's our first game here, is naming points 4 different ways. All right, the next game is changing from xy to r theta. Now, we're already experts at that because we've done the trig form. So we have r is Pythagorean theorem, square root of x squared plus y squared. And theta is the inverse tangent of opposite over adjacent, so y over x. Now, if I have r and theta, I can get x just by going r times cosine of the angle, and I can get y by going r times sine of the angle. Okay, so that's it, piece of cake. Cruising onward. Okay, so what we want to do now is take -3, 4 and put that in polar coordinates. All right, so you know that 3, 4, 5. So you know it's going to be 5 comma something. And so all we do is take inverse tangent of 4/3, because notice we're looking right here. Left 3, up 4. And there's my theta. Now, we go to the calculator, and we go, now we want it in degrees, so we go to mode, and we change radians to degrees, and then we go inverse tangent of 4 over -3. Now, your calculator is going to give you -53.13 degrees. That's down there. Well, the problem with your calculator is it doesn't know the difference between +4 over -3 or -4 over +3. So it basically gave you the angle down here, but you want the angle up there because you know it's left 3, up 4. So you have to add 180 to this angle in your calculator to get it up there. And so that gives you 126.87 degrees. Okay, so there's your magnitude is 5 from Pythagorean theorem. It's always positive. And your angle, we had to adjust from what our calculator gave us. So never just take the word of your calculator. Okay, so let's try another one. 4 squared root of 2, -4 squared root of 2. So we're going right 4 squared root of 2, and we're going down 4 squared root of 2. Well, so we know we have a 45, 45, 90 right triangle, so that means we know the angle is that 45 degree in the 4th quadrant, which makes it 315. So right away I can go, it's something, comma, 315. Now, the magnitude is always going to be the square root of 2 times either one of the legs. So that just makes it 4 times square root of 2 times square root of 2, which is 4 times 2, which is 8. So that's it, 8, comma, 315 degrees. So it's just a squared plus b squared equals c squared. So we square this, and you get 16 times 2, which is 32. And 32 plus 32 is 64. Square root of 64 is 8. And the angle, like we said, you could do inverse tangent of -4 squared root of 2 over 4 squared root of 2, which would give you -45 degrees. Now we don't want negative 45 degrees, we want 315 degrees positive. All right, now, let's go back the other direction. So we have 5, 240. Now what's the x and the y component? Well, this is going to be, the x is going to be 5 cosine 240, and the y is going to be 5 sine 240. Okay, well, what is cosine of 240? Well, 240 is 60 degrees past 180. So here's my 240. That's a 30, 60, 90 right triangle. So that means this is negative square root of 3 here, and this is negative 1 here, and the radius is 2, always positive. So cosine is negative 1/2. So 5 times negative 1/2 is negative 5/2. And sine is negative square root of 3 over 2. So it's negative 5 square root of 3 over 2. Bam, that's it, game over. All right, now, back to polar coordinates in radians, which you're always allowed to do. And let me just say real quick, we could have expressed this in radians too. If they had said they want the answer in radians, then we'd say, oh, that's 8, 7 pi over 4. Same thing. So you just have to do whatever they tell you to do. Usually, well, yeah, same thing. We could have had that in radians. You'd need the calculator to do that too. All right, so 3 at an angle of 7 pi over 4. Well, let's just look at that. So we've got 7 pi over 4 is down here. And so we've got 1, 1, and square root of 2. And notice this is down, so it becomes negative 1. All right, so this is going to equal 3 cosine 7 pi over 4, comma, 3 sine 7 pi over 4. Well, what's cosine 7 pi over 4? That's positive square root of 2 over 2. So we have 3 times square root of 2 over 2 for the x-coordinate, and the sine is negative square root of 2 over 2, so that makes it negative 3 square root of 2 over 2 for the y value. That's it, game over. All right, now, we have just been converting coordinates from rectangular to polar and polar to rectangular. Now let's convert equations between polar and rectangular. So, x squared plus y squared equals 9. That's rectangular because it has x's and y's. So we want to change this into something with r's and thetas. Well, if you go back to the translations, r is the square root of x squared plus y squared. That means r squared equals x squared plus y squared. So when I convert the equations, it's the same thing. The x squared plus y squared just becomes r squared equals 9. Now, notice I have my equation in nothing but r's and thetas instead of x's and y's. And if I want to simplify it, I could just make it r equals 3, which is basically a circle of radius 3. Okay, what about y equals 5 over x? Well, to make it a little simpler, what I'm going to do is multiply x on both sides. So xy equals 5. Now, x is r cosine theta. And y is r sine theta. So technically, we're finished right there. There's an equation with nothing but r's and thetas. So we can clean it up a little bit, though. R times r is r squared, and then sine theta cosine theta equals 5. So there's rectangular, there's polar. Piece of cake. All right, now y equals 2x. This is an interesting one because we've got, notice what this is going to look like if you graph it. Y equals 2x is a line with slope 2 that goes through the origin. Well, what's the angle? Well, if it's slope 2, that means this is a 2 and that's a 1. And so that means our angle, theta, is going to be the inverse tangent of 2 over 1. So if we let's just go y over x equals 2. All right, now, tangent theta is y over x. Because remember, theta is inverse tangent of y over x. That means y over x equals tangent theta. So if I go back to here, then I have tangent theta equals 2. So tangent theta is the slope of the line. So if you know the slope is 2, then you automatically just say tangent theta is 2. Bam, that's it. Okay. Now we have equations in polar form, and we want to change them to rectangular. Okay, so what we're going to do is we're going to try to get rid of the r's and the thetas and turn them into x's and y's. Well, r equals 4 sine theta. Now, I know that r sine theta is y. So what I'm going to do here is a little trick. I'm just going to multiply both sides by r. Now notice I have an r sine theta, which is y, on the right. And look what I have on the left, r squared. What's that? It's just x squared plus y squared. So I have x squared plus y squared equals 4 times r sine theta, which is y. So that really is our rectangular equation. Now, if we want to put it in standard form, we could say x squared plus y squared minus 4y equals 0. And you're going to find out that's a circle. Okay, now, what about r equals 2 secant theta? Well, I don't know about secant theta. That's a little scary. So what I'm going to do is I'm going to change it to r equals 2 over cosine theta. Now I can see if I multiply cosine theta over to the left, I have r cosine theta equals 2. Now r cosine theta is x. That's it, game over. I have no more r's or thetas. I have nothing but x's and y's, and that's it, x equals 2. So r equals 2 secant theta is basically a vertical line that goes down through x equals 2. Okay, now, what about just plain theta equals pi over 3? Well, theta equals pi over 3, we're going to do, yeah, let's just look at it simply first, is theta equals pi over 3 means we've got an angle that goes 60 degrees. There's pi over 3. And so what I want to do is, I know this is a 30, 60, 90, so this makes this 1, that makes this square root of 3. And so I can just say I've got a line with a slope of square root of 3 over 1. which is y equals square root of 3x. That's it, game over. Now, another way of seeing this is tangent of theta here is square root of 3 over 1. So I could say from theta equals square root of 3, I could say tangent theta equals square root of 3. Now remember, tangent theta is just y over x. So I can change this to y over x equals square root of 3. And if I multiply both sides by x, then I'm back to y equals square root of 3x. So that's it, piece of cake. Now, one last one, r equals 3. So that's going to be a circle with a radius of 3 and the center at the origin. Well, notice I'm really going the other direction from this one. If r equals 3, I'm going to square both sides and make this r squared equals 9. Now, r squared equals x squared plus y squared. That's it, game over. So notice the name of the game here is, if we're going rectangular to polar, you're going from x's and y's to r's and thetas. And sometimes you only have r's, sometimes you only have thetas. And if we're going from polar to rectangular, you're going from r's and thetas to x's and y's. Sometimes you only have x's, or sometimes you only have y's, but that's, you need to just get rid of all your r's and thetas and turn them into x's and y's. Okay, last thing we're going to do is graph these equations. It's not r equals pi over 3, it's theta equals pi over 3. Okay, so I want to graph r equals 4. What that means is I just have a circle that has radius 4. That's it, r equals 4. The radius is 4 in any direction. Now, what about theta equals pi over 3? What's a similar idea? The angle has to be pi over 3. Pi over 3 is 60 degrees. So that's it. It's just a line that goes pi over 3 toward pi over 3 and away from pi over 3. Now, a lot of people make the mistake of only drawing it up to the right and then stopping at the origin. But remember, you have negative values with the pi over 3 angle as well. So there are the graphs of your polar equations. Now, let's crank up the juice just a bit. Okay. We're going to graph r equals 2 cosine theta. Now, just like graphing rectangular equations when you don't really know what they look like, you pick x's and find y's. Well, we're going to do the same thing here. We're going to pick thetas and find r's. So, fortunately, I know my special triangles. And what I'm going to do here is I'm going to pick the angles that are simple. In other words, I don't want to pick pi over 6 because cosine of pi over 6 is square root of 3 over 2, and I don't want to have to get decimal equivalents. So what I'm picking is the thetas that make cosine convenient, and those thetas are going to be the pi over 3, 2 pi over 3, 4 pi over 3, 5 pi over 3. So, and the quadrantial angles, of course. So when I put in a 0 for theta, cosine of 0 is 1, 2 times 1 is 2. I put in pi over 3. Well, cosine of pi over 3 is 1/2. 2 times 1/2 is 1. Now I put in pi over 2. That's straight up, and cosine is right and left. So that's 0. 2 times 0, 0. 2 pi over 3. Well, now I'm going left. And so cosine of 2 pi over 3 is negative 1/2 times 2 becomes negative 1. And pi, cosine of pi, is straight left. That's negative 1. Negative 1 times 2 is negative 2. Well, let's just put this on our graph paper. Okay, so I have 2, 0. Two at 0 degrees, and then I have 1 at pi over 3. So I'm going the pi over 3 direction, and I go 1 up. Okay, then I go 0 at pi over 2. So 0 at pi over 2. And then I go negative 1 at 2 pi over 3. So where's 2 pi over 3? It's up this way. But I go negative 1 from there, so that means I'm going down to here. So 1 away from the 2 pi over 3. And then the last point that I did was negative 2 at pi. So here's pi directly to the left, and I'm going 2 away from that, so I'm basically back where I started. Now, if I wanted to, I could get some of the angles in between. Like if I did want to get pi over 6. See, I'm missing something at pi over 6. I'm not quite sure what shape this is in here. So at pi over 6, cosine of pi over 6 is square root of 3 over 2. And 2 times square root of 3 over 2 is square root of 3. And square root of 3 is about 1.7. So I'm going 1.7 right about here. Bam. And then I know that cosine of the angle down here, negative pi over 6, would be also 1.7. And so what I see then is I have a circle. With center 1, 0. So basically that's how you graph your polar functions. Just pick convenient points and put them on the graph. Yeah, let's do this one. So 2 plus 2 sine theta. Now, remember, sine theta, I'm going to pick the things convenient for sine, which is pi over 6, 5 pi over 6, 7 pi over 6, and 11 pi over 6, because I'm not dealing with square root of 3 over 2. Okay, so sine of 0 is 0. 2 plus 0 is 2. Sine of pi over 6 is 2 times a half is 1. 2 plus 1 is 3. Sine of pi over 2, well, that's pi over 2 is 1. So I have 2 plus 2 is 4. Then 5 pi over 6, I'm back to 1/2. So 2 plus 1 is 3. Then sine of pi is 0, so it just becomes 2. Sine of 7 pi over 6 is negative 1/2, so I have 2 minus 1, which is 1. And sine 3 pi over 2 is going to be negative 1. So I have 2 plus negative 2, which is 0. And then sine 11 pi over 6 is going to be negative 1/2. So 2 minus 1 is 1. Now I'm going to put those on the graph and see what they look like. So first point is 2 at 0. So 2 at 0 degrees. Okay, then 3 at pi over 6. So here's my pi over 6, and I go 1, 2, 3. And then I go 4 at pi over 2. 4 at pi over 2, 4 straight up. Then I go 3 at 5 pi over 6. So 5 pi over 6 is this direction. I'm going 1, 2, 3. Then I have 2 at pi. Then I go 1 at 7 pi over 6. So 7 pi over 6 is this way, 1 is right here. Then 0 at 3 pi over 2. So basically it's straight down at 0. And then 1 at 11 pi over 6. So 1 at 11 pi over 6, right there. Now, this is kind of a strange shape. It's like a circle that's been dented. So here's the top part of it. Now, what's going on in here? Well, it's going to just continue toward the 3 pi over 2 in both directions. So this makes what we call a cardioid, because it looks like a heart. And I don't mean like a Valentine's heart. I mean like an actual human heart, like the organ of the heart, cardioid. There it is. Okay, so that's basically all you need to do is you take your polar equation, you pick thetas that make the sine or the cosine function convenient, you plot a bunch of points, and if the ones that are convenient aren't enough, then you do a couple that are a little inconvenient, and then you get the basic shape, and then you're in the money, and have fun with these.